All right, everyone, we are going to continue our considerations. Basically, what we're going to do is we're going to look at further properties of Wiener processes. First off, we're going to look at the distribution again, summarizing some basic things. Then at the increments, which are actually independent of each other. Then we later are going to check the so-called Martingale property, basically illustrating that the process is a Martingale. Then we're also going to look at the so-called Markov property, which I haven't addressed before. And then some other properties basically include the scale rule, which is basically looking at the invariance of the scale of the process. And after that, we're going to look at some basically functions of Wiener processes that illustrate some basic applications. One of them is basically the Brownian motion, which we have seen before. The other one is going to be the Brownian motion with the drift. This is just simply actually corresponding to the random walk with a drift. Then later we're going to look at the so-called Brownian bridge, then the so-called reflected Wiener process. Then you have a geometric Brownian motion, which is a very common one, especially in finance. And then we have also the maximum Wiener process, which you're going to look at, and finally the integrated version. Now the Wiener process is already an integrated process, but that doesn't matter. Basically, this will have another integration order. Anyways, this is it. Okay, so that's going to be shorter, a little bit shorter than usual. Okay, we're going to start with basically recalling the properties of a Brownian motion again. A Brownian motion is simply just a stochastic process. You see, this is a continuous time stochastic process that is satisfying the following properties. The first property is that the starting value of the process is going to be 0, at least almost surely. We talked about that, so just wanted to basically have that repeated. Second, the increments of the Brownian motion are independent. Third property is that it has almost surely continuous parts. And that's pretty much it. And the last is basically that it is following the normal distribution in terms of a random variable, where the mean is going to be 0 and the variance is actually proportionate to time. Sigma squared basically was the variance of the noise from which the corresponding random variable, basically random walk was constructed from. Now, if sigma is equal to 1, which is also basically equivalent of saying that the sigma squared is equal to 1 in this case, then the Brownian motion is said to be the Wiener process. And we're going to look at that basically in more detail as we looked last time. We're going to denote the Wiener process by capital W, and that is basically a time point t. And we simply just basically also established the relationship between the two. So 1 by the square root of the variance of the Brownian motion is going to be, times the Brownian motion is going to be actually the Wiener process. So this is a way just basically standardizing a Brownian motion. You can also call it the standardized Brownian motion, by the way. That's pretty much it. One of the properties that we looked at basically was the quadratic variation, and as well as the absolute or slash total variation, which we're not going to recall now. So we're going to basically move on a little bit. We're going to look at further properties, which I want to summarize here. Okay, so we have a Wiener process denoted by W, and then the first property is that what I wanted to address is the Gaussian distribution, not just basically for the process itself, but also for its increments. So let's say you have the process at time point t minus a time point s, where t is not less than s. It is also going to be normal, where actually the mean is going to be 0 and the variance, however, is going to be t minus s. Okay, it should be denoted that t is not supposed to be less than s in this case. We also need to understand that the increments are uncorrelated. So not just independent, but also, of course, uncorrelated. If random variables are independent, they're also uncorrelated, which means that the autocovariance is going to be actually okay, that's not basically translated to the increments directly, because there is going to be autocorrelation of the process, but not regarding their increments. The autocorrelation of the Wiener process at different points of time t versus at time point s is going to be the minimum, just as basically the case was for the corresponding random walk. I'm not going to basically look at the random walking again. Okay, so it should be actually denoted that, again, s is not greater than t in this case. So if s is not greater than t, of course, and simply less than that, this is going to be s for sure. Now I want to basically confirm that a little bit. So the covariance, or the autocovariance in this case, is going to be the expectation of the product minus the product of the expectations. Now it should be denoted that the Wiener process has the expectation 0. So this means that the autocovariance is going to be equal to the expectation of the product of the two at different points of time. Now, as we basically look at that, just basically copying it here, I'm going to look at in terms of the increments now, because if s is less than t, then it should be actually been written down differently. So you look at the increments first, plus the process. So the process at time point s minus the process at time point s should be actually cancel itself. As you can see, this is just the same thing, which is actually simply just your, a zero addition, if you call it like that. Whereas at time point t minus at time point s, this is the increment of the process at time point s, of course, and the increment of the process at time point s for time point t plus the process at time point s is going to yield actually the process at time point t. Okay, you can put that in brackets if you like, which I'm going to, because I'm going to multiply the two. So if you multiply basically the process at time point s with itself, this is going to be its square. That's not difficult to see. And then after that, I'm going to multiply the increments by basically the process at time point s. Now, if you keep the increments, I'm going to write it down here. So this is the increment of basically of the process at time point s, or you can say at time point t, of course, because t minus s, you have basically looking at increments at a different point of time. And now I'm going to write down basically the process at time point s as in terms of its increment, basically from time point 0. So you have the process at time point s minus the process at time point 0, because the starting value is at least 0 almost surely. So this is actually an equality which is true at least almost surely. Now the two increments here at, let me repeat, at time point s and as well as at time point s are independent from each other. This should be kept in mind basically when we look at it. Now I'm going to split the sum, because the expectation of a sum is going to be the sum of the expectations. So first you have the expectation of the square, which is here, and then plus the expectation of the product here of the two increments. Okay, so I'm going to just simply copy it and writing it down. And then again, since the increments are independent from each other by definition, this means that the expectation of the product is going to be 0, because they're also going to be uncorrelated. So this is basically just generating to the expectation of the square at time point s, which is going to be actually s, because that's basically its variance. So the expectation of the square minus the square of the expectation would be its variance, but the expectation is 0, so the expectation of the square minus the expectation minus the square of the expectation will simply just degenerate to the expectation of the square, which is its variance, by the way. And the other part is going to be simply just 0, because the increments are independent of each other, from each other. They're not overlapping. Even if basically this is the increment between time point s and time point t versus time point s and time point 0. They don't overlap with each other, so this is basically what it yields. And since s is less than t, this is actually confirming the result that the covariance of the process at time point t versus at time point s is going to be the minimum of those two sampling points. Now, what has that to do with the uncorrelatedness of the increments? This is basically referring to the uncorrelatedness of the increments, because the increments between time point s and time point t do not overlap with the increments from time point s to time point 0. This is it, okay? And the third property which I'm going to look at, and which we haven't done before, is the non-differentiability of the paths, at least almost surely. Now, a function is called differentiable if its derivative exists. And we're not going to prove this directly, but we're going to look at basically the differential quotient. So this is the increment at time point t with respect to time point s, of course, divided by basically the difference between the sampling points, which would actually converge to the derivative of the process. It would be existent at least almost surely, but it cannot. And the issue why it cannot is because the variance of this expression, so if you look at that, now the expectation would be 0. This follows a normal distribution, by the way. The expectation is 0 because the expectation of the increments would be 0. So that is for sure. T minus s is just actually a constant, so 1 by t minus s is actually what you're multiplying that with. And since the variance of the increments is going to be t minus s, as you see, which is also multiplied by 1 by t minus s, which should be squared after all. So t minus s by the square of t minus s is going to yield 1 by t minus s, as you can see. And this is going to be finally the variance of this expression. And this tends to infinity after all, as basically s tends to t. Okay, so as basically the sampling points are getting closer to each other, the variance of this expression is going to diverge. And since the variance diverge, which indicating that the process is not differentiable, because if it was, then at least the variance would not diverge, but it does, and that is the reason why. Okay, that's not proving it, basically, the statement, but that's simply just illustrating it without looking at mathematical depth. All right, or with basically medical depth, if you say. Anyways, so that's basically the standard properties, and in addition to that, we were also looking at the finiteness of its quadratic variation, which I'm not going to recall now. That was part of the previous lecture. We're going to talk about that when we look at Ito's lemma in the following lectures. Next, we're going to look at, however, the Martingale property of the Wiener process, which we haven't addressed before. A martingale is simply just a process for which its best predictor would be equal to the current observation. Okay, so the Wiener process is going to be a martingale, and this means the following. So the conditional expectation of the process, or first off, the expectation of the absolute value of the process is supposed to be finite. This is the first property that Martingale has. I'm just basically recalling it right now, but in context of the Wiener process, this is what is supposed to be shown. And the second property is that the conditional expectation of the process for some future value, given its past, which is represented by the filtration at time point t. So ft is supposedly be a filtration consisting of the families generated by the paths of the process. So I'm going to basically address this issue here. So ft is actually a sigma algebra at time point t, which is generated by, so sigma of something, which means that you're addressing a sigma algebra generated by something. So this is not basically to be confused with the variance or the standard deviation of the process. So sigma as a function is addressing a sigma algebra which is generated by some sort of random variables which are listed here. And basically I will basically address the Wiener processes at previous points of time. So let's say time point t is a current point of time, and time point r is some previous point of time or a current point of time. Anyway, this represents the past of the process, or the total past. And this is basically conditioned on some future observation, because h is supposed to be greater than 0, which means that t plus h is some future sampling point. And the conditional expectation of some future sampling point, some point time in the future, is going to be given by the current observation of the Wiener process, given its past at time point t, as well as its current observation at time point t. And that is basically what the statement should be. Now we're going to show both of them, and I'm going to start with calculating the expectation of the absolute value of the process. And the question is how to. And I want to recall the so-called transformation theorem by which I'm doing that. First off, I'm going to review how to calculate the expectation of a random variable at first, which is supposedly be a continuous one. So the expectation of a random variable, which is a continuous one, is supposed to be the integral from minus infinity to plus infinity of x times its density at time point, or at point x with respect to x. So the integrator is x now. X times the density is going to be the integrand, and the integral is supposed to be calculated on the total domain of the set of real numbers. Now, if you do this with where you would apply a function, so we'll look at that, we're not basically calculating the expectation of the Wiener process. We are calculating the expectation of a function of the Wiener process. This addresses basically the transformation theorem, and all you would need to do is just basically put x into that function. And that's pretty much it. So if you want to address basically the expectation of the absolute value of the Wiener process, you could do this by using the density of the Wiener process, which is going to come from the normal distribution. From minus infinity, looking at the integral from minus infinity to plus infinity of the absolute value of the integrator. I'm calling the integrator y this time, so it's going to be the absolute value of the integrator times the density of the Wiener process, which does not need to be transferred in this case. Now, what is the density of the Wiener process? Now, since the Wiener process is a Gaussian, and you can call it basically a random variable, because at time point t at least it would be actually a random variable, strictly speaking, if the time point t is fixed, you would need to use basically the Gaussian density where the mean is 0 and the variance is going to be sigma squared times t. So this yields 1 by the square root of 2 times pi times times t, this case, okay, because the Wiener process has, I mean, when you look at sigma squared, which was coming from the Brownian motion, this is going to be equal to 1. So the variance of the Wiener process at time point t is t basically. And then you have e to the power of minus 1/2 times basically the integrator, which is going to be the square of the integrator minus 0, which is simply just y squared in this case, divided by 2 times t. Okay, so keep in mind basically that the expectation of the Wiener process is 0 and the variance of the Wiener process is t, and this reflects basically the Gaussian density here. So this is the Gaussian density of the Wiener process, which is multiplied by the absolute value of the integrator, because that's all you would need to do when you apply the transformation theory. Next, we're going to look at this integral closely, or basically the integrand closely, because what you need to address here is that, or you might be recognizing it, that this function in purple, which is called the integrand, is a symmetric function. And this is a symmetric function with respect to the y-axis. So which means that if you interpret the integral to be an area of this function from minus infinity to plus infinity with respect to the x-axis, even if the integrand is called y, but it doesn't really matter, you should need to understand that since this function is a symmetric one, which I'm going to show you now, why, because the function at point minus y, which would yield basically the absolute value of minus y, which is y, by the way, or the absolute value of y, because they two are identical, times 1 by the square root of 2 times pi times t times e to the power of negative minus y squared, which is actually also y squared, by the way, divided by 2 times t, is equal to that. So these two expressions are equal, which means that this function, the pink one, is a symmetric function, and that is a symmetric function with respect to the y-axis. So we basically with the ordinate, which is illustrated here. So the same thing would come out if you put in y into basically as the argument instead of negative y. So basically we're summarizing it here. So this means that the integral basically between minus infinity and 0 of this function is just as large as the integral from 0 to plus infinity of the same function. So I'm going to take that twice. So you have 2 times the integral from 0 to plus infinity instead of basically integrating the functions from minus infinity to plus infinity after all. So the integrator will only take values between 0 and plus infinity and not between minus infinity and 0, because the integral on the left-hand side of the ordinate is going to be just as large as the integral on the right-hand side of the ordinate. So 2 times the integral of the function between 0 and plus infinity is just going to be just as large as basically the total integral here from minus infinity to plus infinity of this function. Now what I'm going to do in addition to that, so I'm going to basically do 2 steps here, is that I'm going to take out the constant. So 1 by the square root of 2 times pi times t is going to be taken out from the integrand, which can be done, which means that basically the integration is a homogeneous function. And then you're left with basically e to the power of y squared, e to the power of negative y squared by 2 times t, and then you have y instead of just the absolute value. So you get rid of the absolute value y, because the integrator will only take values between 0 and plus infinity. So you have, instead of just basically the absolute value of y, you simply just transform it to y, because the integrator is not negative now. So 2 times the integral between 0 and plus infinity of this function, which is the integral here, times 1 by the constant, by the way, is going to be the same as the integral above. So you get rid of the absolute values, and then you get rid of basically the negative value for the integrator. So this integral starts at 0.0, and this is basically a little bit easier to deal with. Now, the antiderivative of this function, which I'm going to address. So first I'm going to keep the constant. So 2 times the square root of 2 times pi times t, which can be simplified a little bit, but I'm going to do that afterwards, times this integral is going to be equal to the antiderivative of the pink function now. And what is the antiderivative of the pink function? At point plus infinity minus the antiderivative at point 0. The antiderivative of this function can be easily obtained, relatively speaking, by integration by parts, which I'm not going to do now. So since I'm familiar with this expression, I'm going to reveal what it is, but you would not need to. So this would not be basically part of the exam, whereas you would see directly what the antiderivative of this function would be, because it might not be clear for everybody. So in this case, if you're kind of struggling with integrals, I will give you the antiderivatives. But later we're going to confirm this. We're going to calculate the antiderivative at point 0, and we're going to calculate the limit, or at least basically its limit, where the argument would basically tend to plus infinity after all. And then we're going to subtract the 2 expressions from each other. But I'm going to reveal what it is. The antiderivative of this pink function is going to be minus t, because we're with respect to y, of course. So I'm would basically integrate the function with respect to y now. Minus t times e to the power of negative y squared by 2 times t. If you ask yourself why this is, okay, where is basically y, would not need to be basically addressed this by the product rule, and the answer is no, because you would do integration by parts. So I'm going to confirm this. I'm going to take basically the derivative of that with respect to y. So I'm going to differentiate this function here, what you see here in yellow now. So to confirm that the derivative of the yellow function with respect to y, not with respect to t, but with respect to y, is going to yield the pink function above. Okay, so I'm going to just simply copy that. Now, here you have minus t, which is a constant, y, because you're differentiating with respect to y now. So this means the constant times a function is going to become the constant times the derivative of a function. So negative t times the derivative of e to the power of minus y squared by 2 times t is going to be obtained by the chain rule. The derivative of the other function is going to stay the same, because the derivative of the exponential function is going to be the same. Okay, this is the first step. Then the second step is putting in back the inner function into that other derivative, which is e to the power of negative y squared by 2 times t. and then you multiply this thing, the whole thing, by the inner derivative. The inner derivative would be basically the derivative of the inner function with respect to y. Now the derivative of the inner function with respect to y, since you have y squared, the derivative of y squared would be 2 times y, and then you multiply it by a constant which is -1 by 2 times t. So this yields actually times negative, and then you have basically the denominator 2 times t, which is multiplied by the derivative of y squared, which is 2 times y with respect to y, of course. So this is going to be actually the derivative of this function with respect to y, and this is equal to the pink one. How come? Because if you basically, and first off, you can cancel -1 here, so that's going to disappear. Then you cancel t, which you can do, or you can cancel 2, of course. I mean, you can also do that, and then you would cancel t, so then you would see that e to the power of blah 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 times y is the same function that you see above. So this is basically what I'm going to write down again as a confirmation. So as you see, this function that you see is indeed an antiderivative of the pink one. Forget about the constant, because you're going to calculate this from -infinity to, or basically the antiderivative, the at point -infinity, if you say that, then minus the antiderivative at point 0. Now if you look at that, this expression, keep in mind this is a power, and this is the exponent of it, and the exponent is supposed to converge to infinity, but it's going to be negative. So then the whole exponent is going to diverge. It's not going to converge, because convergence to infinity does not exist, but it is going to diverge, okay, to basically to -infinity. And so thus, if you, I mean, okay, can you keep the constant first? Constant times basically the primitive function, or the limit of the primitive function, whereas y would tend to +infinity, so then y squared does the same thing. So I'm going to put it in here, okay, but the exponent will be negative, so the exponent would basically tend to -infinity, and e to the power of -infinity would this would converge to 0. So then you would have basically 0 coming out for that limit. Okay, I was not writing that down, but if basically y tends to infinity, the whole thing would basically tend to 0, because -t times e to the power of, let's say, quote unquote, -infinity would be -t times 0, which yields 0. So that's basically what comes out if you look at the antiderivative at the upper endpoint, which is not an endpoint, but it could be, technically it could be the case though. Okay, and then you would subtract the antiderivative at point 0. The antiderivative at point 0, all you would need to do is just to put in 0 into the antiderivative for y, of course. So this means that you have y squared, which is 0 squared after all. So -0 squared by 2 times t is going to be 0, and e to the power of 0 is going to be equal to 1. So then you got -t times 1 coming out, and that is need to be subtracted from basically from the upper end point, or the antiderivative, let's say at the upper end point, which is a limit, by the way. And this would be basically it. Okay, so 0 minus -t is the antiderivative, or the limit of the antiderivative, where the argument tends to 0, tends to infinity, minus the antiderivative at point 0, and that's it. Now 0 minus -t is going to be t finally, so you get your constant times t, and that's pretty much it. Okay, and now I'm going to clean it up a little bit. So you can do, what you can do is, of course, 2 times 2 by the square root of 2 is going to be the square root of 2, of course, right? So you can write just down 2 here under the square root is going to be fine. Then t by the square root of t is going to be the square root of t, which is, okay, written like this. And then you got pi in the denominator under or beneath the square root, which is here. So that's going to be the expectation of the absolute value of the Wiener process. Now this is going to be finite, of course, so that's basically what is required to do to confirm the Martingale property of the first Martingale property of the Wiener process. This expression has to be finite, so the absolute value has to be finite, which it is, which also indicates that the variance is finite, but that's just a side note here in this case. Okay, it is finite if t is given. If t is given, of course. If t is not given, then it's not, but it doesn't need to, because t is supposed to be a specific point of time. And then I'm going to look at the conditional expectation of some future observation given the past. So anytime you see basically a sigma algebra like this, which is coming from or supposedly coming from a filtration, this means that basically given the total past, including the observation at time point t, because that is not random anymore. Now, however, we're going to look at this expression, so I'm just basically keeping that as is. Okay, so all I was doing is copying it, and I want to have some increments in there. Okay, so I'm going to take basically the observation at time point t and subtracting it, so this would basically just eliminate itself. But given the past at time point t, this observation is known already, and so thus I could basically take that out from the expectation operator, and since the increments have expectation 0, this confirms that the conditional expectation of the Wiener process for some future observation at time point t, so given a current observation at time point t, but not just that, given the past also, this would be simply just, okay, I will split that into two parts. So first off, the expectation of a sum is the sum of the expectations, so I was splitting that. Here you see the increments, astrically, the increment at time point t plus h. I assume that basically h is some positive constant, which has been addressed in the statement. And since the increment, and the increments does not even depend on the past, by the way, in this case, because they don't depend on anything. But the expectation with that would be also 0. Now the expectation here, as you can see, if the past is given, that's going to be the constant. So this is just a constant observation if the past at time point t of the process is known, and the expectation of the increment is always 0. Even if basically the past is not given, that would be actually also 0, and then basically this would be it. So this means that the conditional expectation of the Wiener process at some future point of time, again keep in mind this is not on this slide, but h is some positive constant, is going to be the current observation itself. This is basically confirming the Martingale property, and that's it. Now, since the expectation of the absolute value is finite and the conditional expectation is equal to the current observation, then this confirms that the Wiener process is indeed a Martingale. Now, in addition, I'm going to also address the so-called Markov property of the Wiener process, which I haven't done before because I was not defining it. But this refers to basically for a so-called Markovian process or Markovian stochastic process, which is also known to be the so-called Markov chain. Markov chain is a Markov process, and a Markov process is a process that satisfies the so-called Markov property. Now, the Markov property is that the conditional expectation, I'm going to show you why, okay? So given the past of the process, again, the conditional, not the conditional expectation, sorry, the conditional distribution or the conditional probability, let's say, of some future value, okay? Not basically being greater than some constant, let's say, which is actually, you can say, this is the cumulative distribution function of the Wiener process at time point t plus h given the past, which is basically what this expression means. Okay, so this is the cumulative distribution function at point w, all right, basically of the Wiener process at time point t plus h given the past. So this is the conditional distribution. Is supposedly, so again, I'm going to tell what it is. This is basically the sigma algebra generated by the past of the Wiener process. Is supposedly be equal to, and h is a positive constant, is supposed to be equal to the conditional distribution of the Wiener process at the same time point, okay, not exceeding basically the same argument, which is W, given just the current observation. And the current observation is supposed to be fixed. So because this expression cannot, you could not have basically a random variable here, so conditional distribution is assuming that in this case, the current observation is fixed, because that is supposed to be the case for every omega from the sample space. And this is basically what the Markov chain is. So this simply claims that you don't need the total past. Basically, the future distribution, okay, which is addressed by the cumulative distribution function of the Wiener process, given the current observation, would be enough. So the current observation would be enough. You don't need the total past of the process to address the distribution of some future observations. And that's basically what the so-called Markov property is. Now we need to prove that. Okay, so for basically for the Wiener process, I was not defining this because I don't use that quite frequently. However, basically this is supposed to be the case. So you don't need the total past. You simply just need the current observation if you basically want to, let's say, predict the distribution of some future observation here for the process. But that's basically what the Markov property would be. Okay, so I'm going to prove this here down below, that these two things are equal, and the question is how to. Now let me start by basically addressing that expression. Okay, so basically what it would be. Okay, here it is. So let's say given the current observation, so let's say, and I'm going to use the increments now. So let's say if the current observation, which is the observation at time point t, so if I say current, I mean basically the observation at time point t, is already fixed, which is supposedly denoted by basically the equality here, that the process at time point t is equal to some constant here, then you can just simply transfer this expression by using the following. So I'm going to write it down again, okay, and I'm going to subtract basically the value at time point t, because since these two are equal, okay, so I was already manipulating the inequality here inside the basically the probability of the event here. I will need to do the same thing on the right hand side, and then the condition disappears because I was already addressing the condition, so I basically was applying it. And what you see here is the increment, and the increment is not supposed to basically exceed this expression, and we'll look at the probability of that one, and that's pretty much it. This is just degenerating to the unconditional distribution. This is the increment of the process at time point t plus h from, let's say, time point t on. And yeah, that's basically degenerating to the unconditional probability that the increment is not greater than w, which was basically the value here, minus the constant, which is the current observation of the Wiener process. Now I would have basically move on, because just copying this expression first, so I was copying it. The increments don't depend on anything, not even basically on the past. So the conditional distribution here, which is, you can say that the this is actually the conditional cumulative distribution function of the increments of the process at time point w minus v, is supposedly be equal to, this is the unconditional one, this is supposed to be equal to this conditional distribution, because the increments are independent. And if they are independent, they are also independent of the past of the process. So this probability will equal to that, and then you could simply just basically move back the whole thing, because since actually the observation at time point t of the process is equal to v, you could simply just basically add it to both sides of the inequality. Okay, so since basically those two are equal, given that, okay, so which we already know, so if that is true, by the way, they simply just make it disappear, and showing that basically what the Markov property is, namely that the conditional distribution, cumulative distribution expressed by the cumulative distribution function of the process for some future observation is going to be exactly the same as the conditional distribution of the process given just one observation, which is the current observation. So the current observation would be enough. It doesn't change basically anything if you look at the total past instead of just looking at the current observation. And that's pretty much it. This was actually the Markov property that the Wiener process also has. Now, I'm going to look at further properties, and this is the last one in this case. Is addressed by calling it scale invariance, addressing basically two different random variables having the same distributions. However, they're not equal, at least not equal almost surely. So the first is basically that the distribution of the Wiener process at time point t, so if time point t is fixed, then it is a random variable, it's going to be normal. Whereas the mean is 0 and the variance is of course t. Now, if you substitute t by sigma times t, you would need to substitute the variance, which is going to be sigma times t after all. And that's basically changing it here. So the distribution is going to change accordingly. Now, this is basically true on the one hand, and the other hand is that the Wiener process at time point t, since it has the normal distribution with mean 0 and variance t, will have the same distribution if you multiply it by same distribution as above by the square root of sigma, which is actually just enhancing the variance, which is actually, as you saw, relates to the Brownian motion, by the way. But that will have the same distribution as this random variable given at time point t, which again the distributions are equal. And why the square root of sigma? Why not sigma, by the way? And the answer is because the variance is actually, if you multiply a random variable by a constant, the variance is going to be the constant square, the square of the constant times the variance of the old one. It's going to be basically quadratic. Okay, so the variance of a linear transformation is not the linear transformation of the variance. However, the variance of a random variable times the multiplicative constant is going to be the square of the multiplicative constant times basically the variance of the old random variable after the transformation. So this expression will have the same distribution as this one above. Now, just because two random variables have the same distributions, it doesn't necessarily mean that they're equal. They're actually not. At least not almost surely. I mean, almost surely not. That would be basically the correct term or the correct way to expressing it. Yet they have the same distribution. So if two random variables have the same distribution, I'm going to denote this by using this tilde sign here. Okay, so this random variable will have the same distribution as the other, but they're not necessarily equal. They're actually not, in most cases at least, almost surely. Almost surely means in probability 1, by the way. But this is something we already know. Anyways, okay, so that should be basically reminded. Okay, so you could not simply just get one by multiplying basically the Wiener process by a constant, by the way. Okay, so that will not yield the observation at this time point by simply just multiplying it by a constant, which will not get you anywhere. Okay, so keep in mind inside the parentheses you'll have the time point, which is addressed here. Okay, so 2 times, let's say, the Wiener process will not be, current observation would not be basically the observation, let's say, for, I mean, you can see this here, this is the square of time point 4 times the previous time point, so in 4 years. Okay, so let's say the current observation in 2 years, and the 2 times the current observation at the basically will not be equal to the observation in 4 years now, if basically the current observation is given in years. Anyways, okay, but they'll have the same distribution, by the way. Okay, but that's just a different story. Okay, now we're gonna look at in the second half we're gonna look at some functions. based on Wiener processes. The first, which we're already familiar with, is the Brownian motion, because I was defining the Brownian motion first. But if you want to basically create a link between the Brownian motion and the Wiener process, in this case, you would simply just multiply the current observation of the Wiener process by some constant to get the Brownian motion. And again, the square of the constant is going to be the factor by which the variance of this process is going to be increased, all right, or actually by or to that of the Brownian motion. You already know that. And yeah, so this is just simply a positive constant in this case. And there is going to be, without loss of generality by the way, and there is going to be also accordingly a Brownian motion with drift. So I'm copying just a Brownian motion first, and then I'm going to address a drift parameter to it, which is also multiplied by time. Why? Because you might remember this from the random walk. If I add basically a drift, a constant to the random walk, and I sum it up, okay, so building basically the cumulative sum of those random walks, because keep in mind guys, that not from the cumulative sum of the random walk, the cumulative sum of these noises, which would actually basically are affected by the random walk. Then you also add up the constant cumulatively. And if you add the constant cumulatively, basically during the whole period, this is basically what it's going to reveal. And I would like you to review basically Donskir's theorem to confirm this. Okay, so that's going to be the Brownian motion with drift, whereas in this case, this is without. Now, it doesn't change that much, only the distribution, but I'm going to show you first, okay, how these two relate to each other. If you look at some paths. Now, first off, addressing the distribution, the Brownian motion will follow the normal distribution with mean zero. Okay, so standard Brownian motion without a drift. And then the variance is going to be increased by the square of the constant here, sigma, accordingly. So that's going to be the square of this basically here. And the variance of the Wiener process is t, of course. So this is going to be the square of sigma times t, which is going to be the new variance of the Brownian motion. We talked about that basically by the definition, of course. And sigma squared is actually was the variance of the noises from which a random walk was constructed from. And then, of course, we're looking at the rescaled version, diffusively rescaled version of the random walk, yielding basically the limiting distribution to the Brownian motion itself. Now, since basically the variance does not depend on additive constants, which is an additive one here, the Brownian motion with drift will have the same variance as the Brownian motion without, but the mean is going to change because the mean is going to be increased indeed. The expectation of a linear transformation is a linear transformation of the expectation. So you simply just need to address the expectation of the linear transformation. This is the linear transformation of the Wiener process. The Wiener process has zero mean, so thus it will basically be the expectation of the Brownian motion with drift is going to be mu times t, and the variance is going to be the same because the variance of a random variable, if you basically fix the time point, and it can be looked at basically the process at time point t to be a random variable, degenerating to a random variable, the variance does not change. So it will be the same as it was for the Brownian motion without a drift. Now, I want to basically look at the path of the processes. First off, I'm going to look at some paths of some Wiener process which are simulated accordingly, okay, which is not actually the Wiener process. This is just an abstraction, by the way, because, you know, based on Donskir's theorem, that will be just simply just a limiting process, whereas basically with a limiting distribution, but in comparison it should be fine. And then I'm going to add the Brownian motion to it, where I will basically take the constant to be 0.5. So that changes basically just the amplitude of the process, as you will see. The dashed line here, the red one, is the, as you will see, the Brownian motion. So I'll basically cut the amplitude of the Wiener process with respect to the y-axis by half, because It's 0.5 times the Wiener process. It would be 2 times it of it, then it would be just basically double it. But that's basically how it changes. Now, if I go back and I would also look into the other process where there is a drift, okay, then this will be simply just evolve around a linear trend here. So I will also add a linear trend, not just basically multiplying the process by 0.5, but also adding a linear trend to it. I'm going to look at the path of the Wiener process again, which is the same as I used in the previous case. Then I'm going to basically add the linear trend to it, which was 2 times, in this case, in my basically simulation, it was 2 times t. So this is just simply just, you know, this linear trend. And then you'll have, again, so the new parameter is just simply 2. And after that, you will add it basically to the process. So you have basically 2 times t plus the Wiener process. Sigma is not changing here, so sigma is equal to 1. And I simply add this linear trend to this process to get the new process here. And that would be it. Okay, so that's simply just adding it here, this linear trend to the black one to get basically the red one, which is shifted, of course, right? It's shifted. Keep in mind the variance of the red one is the same as the variance of the black one, by the way, but the expectation is not. The expectation of the black one would be 0, whereas the expectation of the red one would be 2 times t after all. All right. Okay, so this is how it looked. Now, we are actually already familiar with that, except for the case where you have a linear trend added to the Brownian motion. But next, I'm going to address the so-called Brownian bridge. The Brownian bridge is simply a stochastic process, just characterized as follows. It is simply just, I mean, in this case, I'm going to look at the process between 0 and 1, the time points between 0 and 1, without loss of generality, by the way. So this is going to be the Wiener process at time point t, then minus, and then you got t times the Wiener process at time point 1. This means that the process will go back where it was or where it was starting from, and that's why it's called the Brownian bridge. So this is basically calling that the name, that Brownian bridge. This is it. Okay. So I'm going to look at some properties for that first before I'm looking at the path. So the first off is that the starting value is, which is 0 almost surely, is going to be also the final value of the process. So the process will go back to where it was coming from. That's why it's called the Brownian bridge, and which is 0, by the way, almost surely at least. So it starts at point 0 and it goes back to it almost surely, based on this expression. It's not difficult to see, because if you calculate the process at time point 1, then you will find that this is going to be, that would be the Wiener process at time point 1 minus 1 times the Wiener process at time point 1, which would be 0 actually almost surely. Second, I'm going to look at the expectation of the process. The expectation of this process, however, is the expectation of that. So this is the just basically, you know, the process itself, which I'm going to look at here. And then after all, the expectation of a difference is the difference of the expectations. So that goes down to the expectation of the process minus, and then you got the linear transformation, or looking at the expectation of the linear transformation, which is the linear transformation of the expectation. And you're left with basically the expectation of the process at time point 1. Now both expressions are 0, of course. So that would mean basically the expectation of the Brownian bridge is also 0. It's not difficult to see. That was a little exercise which I did here in this case. And as your exercise, I want you to basically to ask you to calculate the variance of the Brownian bridge. The variance of the Brownian bridge is going to be the variance of this expression. However, the variance of a difference, keep in mind, is not the difference of the variances. You would need to look at the expectation of the square of this expression and then take it down, which I didn't. Okay, so in this case, I wasn't doing it. I was just basically presenting here the final result, which is t times 1 minus t, which is, and this is something which it should be denoted, it is less than that of the Wiener process, by the way. Okay, so that is it. At time point 1, there is no variance anymore because the variance would be degenerating to 0 after all. Okay, so that it means that basically the process degenerates to constant. And then, of course, you can also address the covariances, or the autocovariances to be more precise. This is another exercise that I would kind of like you to ask to do. And I haven't done this because it's actually quite boring, but it's a good one basically to deal with expectations and variances and so forth. This is the minimum of T and S, which again is quite similar to that of the Wiener process. However, then you got minus the product of T and S, which you'll have here. So this is going to decrease actually regarding the autocovariance. So the autocovariance is less than that of a standard Wiener process, and so is the variance. The variance is also less than that of a standard Wiener process. Anyway, okay, you can look at the distribution. The distribution is going to be normal still, because the normal distribution is reproductive with respect to linear transformations and also with respect to sums. Of course, you got a difference here, but plus minus t times another random variable at time point 1, of course, would be just a sum, basically, and which you would have basically 2 random variables. And then, of course, again, so since the normal distribution is reproductive with respect to sums as well as linear transformations, it will not change. So in order to establish basically the parameters, which is the mean, as well as the variance, the expectation is of course 0, which can be just taken over, and then the variance is going to be t times 1 minus t, which I haven't confirmed here, but that would be a good exercise which I kindly ask you to do. And that's pretty much it. So this is how basically the distribution of the process will change. Since it goes back, all right, so where it was coming from, the variance or its variance is going to be less than that of a standard Wiener process, where the variance of that would be simply just t. Okay, this is how it looks. So compared to a standard Wiener process, the black one is the standard Wiener process, as you are about to see. And I'm comparing that to the path of a Brownian bridge, which I was using before. So calculating that would be not difficult, which I call x here. X is the Brownian bridge now. So in this case, this is the dashed line, the red dashed line reflecting it. But keep in mind, at point 1, it goes back where it was coming from. It's still not there, but here it is. And that's pretty much it. So the variance of it, of the red one, is less. Okay, now let's go back and move on with the next example, where I would looking at a function, and this is going to be point 4. This is called the reflected Wiener process. This is another one where you would simply just look at the absolute value of the Wiener process. So if the Wiener process is going to be negative, then it will be basically transferred to be positive. And we have already actually calculated the expectation of that, or I was already addressing the expectation when I was looking at the so-called Markov / Martingale property, where actually the Martingale property was relevant. So the expectation of the absolute value is supposed to be finite, because then the variance would be also finite. However, I was already calculating that. So now I'm going to simply just summarizing it. And that's pretty much it. But I was not addressing the variance of the absolute value, which I'm going to. The variance is not going to be difficult, because the variance is the expectation of the squares minus the square of the expectations, which, as actually the case, the square of the absolute value was simply just the square of the Wiener process itself. But that's basically coming next. And the expectation is here. So if I take the square of that, you simply just need to get rid of the square root. And that's pretty much it. The expectation of the square of the reflected Wiener process is going to be simply just the square, the expectation of the square of the Wiener process, which is its variance. So the variance of the Wiener process, which is the expectation of its square, because the square does not change anything, or at least the absolute value does not change anything, is or was t, that was the variance of the Wiener process, and minus the square of the expectations. Now the expectation of the Wiener process is 0, but the expectation of the absolute value is not, where you would have basically the square root of t, square root of 2 times t by pi, and if you square that, you would simply just get rid of these square roots, so that it would be 2 times t by pi, and that's pretty much it. So that is the variance of the reflected one. Although this, as you would see, this is simply just, you can see that this is also less than that of the Wiener process. Why? Because if the process is negative, then it's going to be pushed back. So if the Wiener process is negative, of course, it's going to be reflected. So that is basically how what the reflection is, to turn it back basically to something positive, or at least non-negative here. So that would be basically a decrease of the variance compared to that of the Wiener process. Now, regarding the distribution function, as you see, this is the cumulative distribution function of the reflected Wiener process, although it's not set as such, but it is actually. So we're going to find that one too. This is also a good exercise, by the way, using that of the Wiener process, which I have already addressed, because this is coming from the Gaussian distribution. Now, if you look at the absolute value is less than small x if and only if the process itself, and I'm talking about the Wiener process, is between minus x and x. That's pretty much it. If a number has an absolute value which is less than 4, then the number must be between -4 and 4. And if the absolute value of a process is less than small x, this means accordingly that the process itself, without the absolute value, I'm talking about the Wiener process now, because again the reflected version is simply just its absolute value, must be between -x and x. And since basically these two events, whereas the absolute value of a process is not greater than x, versus the process itself is going to be between -x and x, are equivalent, one implies the other. If this is true, then this is true, and the other one is true. The probability of these two events must be the same also, respectively. And that is just that. Okay, so we're going to basically start from here. The probability that that the random variable takes values between -x and x is going to be the probability that the random variable, or basically the process, is not greater than x, minus the probability that it is not greater than -x, because I'm going to look at the area of the density of the Wiener process between -x and x, and that is the area of the density from -infinity up to t, -infinity up to x, minus the area from -infinity up to -x, because that is the area basically between the two. Now, since actually the distribution of the Wiener process is a Gaussian distribution, right, where the density function is actually a symmetric function, which is symmetric with respect to the y-axis. I'm going to keep that expression first because that doesn't change. The probability, or let's say the area between -infinity and -x is just as large as the total area minus the area up to x. That is basically the issue. So the area left to -x is just as large as the area right to +x. And the area right to +x is the total area, which is 1, minus the area up to x. So this probability, due to the symmetry of the density of the normal distribution, at least the normal distribution, would mean 0, because the Wiener process has the mean 0, will be the total area minus the area up to x. So this is the way to get rid of basically the negative argument here. And then since
minus p, or the probability of that, basically is 2 times the probability of that. You're going to get 2 times the probability of that minus 1. This is going to be the cumulative distribution function of the reflective Wiener process. So this is going to be 2 times the cumulative distribution function of the Wiener process minus 1, which is actually what it is. Now, okay, so I want you to remember that, because I'm going to link that to another process which is going to be important too. Okay, so that's going to be the next one, but I'm going to look at the reflection here. So again, reflection is relatively easy. If the Wiener process, let's say, goes down and is go beyond the x-axis, then regarding its reflective counterpart, which is denoted by the dashed line here, which is the red one, is going to be simply just up to this point. It's just simply going to be basically going back up again, because I'm going to look at its absolute value now. So you can simply just, you know, project the process down here to on basically on this image, right? So you would have basically that one with the red dashed line, and that's pretty much it. Okay, so that is it. And yeah, so that's how you would basically get the reflection back. Okay, that was just one path which was missing. Okay, now I was also addressing the expectation, which I have calculated before. That was square root times 2 times t, the square root of 2 times t by pi, if I recall it correctly, which was here. Okay, so that's basically the square root function here of t. This is it. Okay, so that's basically the expectation around which basically this evolves, and the expectation of the Wiener process is of course 0. Anyway, okay, so that's basically what the reflected Wiener process was. Next, I'm going to look at another one, which is a geometric Brownian motion. Now, the geometric Brownian motion is very, very common, especially in finance. This addresses the distribution of the logarithm. In this case, you simply just recall it, the logarithm of the geometric Brownian motion. So x is the geometric Brownian motion. Now, x is not a Brownian motion. X is a geometric Brownian motion. In case of a geometric Brownian motion, the logarithm of a geometric Brownian motion is going to be a Brownian motion with drift. That's it. So if basically the logarithm of some process, not the process itself, its logarithm, its natural logarithm, by the way, is a Brownian motion with drift, then the process itself is called the geometric Brownian motion. This is very common in finance, because the increments of these processes, so I'm going to look at the increments, right? I mean, later on, later lectures, is going to describe some asset return. So if basically x is describing the dynamics of some asset stochastically, then the increments of the logarithm is going to describe its returns. And that's basically why the geometric Brownian motion is very common. So for a geometric Brownian motion, you have that basically its logarithm is going to be a Brownian motion with drift, and that's basically what it is. Okay, so of course you have those parameters. Mu can be actually, I mean, in this case though, since returns can be negative, of course, but I'm going to assume that this is going to be just non-negative in this case, at least for now. Okay, but sigma is not supposed to be, but again, mu can be negative in this case. You look at basically the original structure of the process. So simply just, this can be revealed by some exponentiation. I was not addressing the starting value here, which again, I mean, what would be actually the starting value, at least for the logarithm? Now, the starting value of that would be 0 almost surely. So in this case, you would have for the geometric, the logarithm would be simply just mu times t. So for its exponential counterpart, in this case, it would be just, you know, that would be a starting value, which is not going to be basically considered e to the power of mu times t after all. But I'm taking that out from basically from the context here. Okay, so this is how basically it evolves, and that is it. Okay, and then of course you'll have the same thing for the I mean, if the starting value would be different. Okay, so you could basically argue that it would be different, but It's actually not, and that's basically how it is evolving. Now, if you compare that to a standard Wiener process, again, the black function, as I use basically for path of the Wiener process, looking like this, then of course the geometric Brownian motion, which is going to be the red dashed line here, or the path of that, it's not just, you know, shifted version of the Wiener process itself, right? So that's not simply just, you know, these distances here are not equal, although they appear to be, but they're not. Okay, it's basically simply just its exponential counterpart, let's say. Okay, so you can see basically that over here. You can also basically make the argument that the starting value would be equal to 1, of course, right? So for the geometric Brownian motion, which again can be different, but it was basically for the logarithm. Okay, so again, I want to make that clear. Okay, so the logarithm would be actually be equal to 0, whereas then in this case, this starting value would be equal to 1 almost surely, because if the logarithm is actually 0, then the exponent is 0, right? So then it would be basically the power would be equal to 1, of course. This is consistent, by the way, but you don't need to have that. Okay, so you don't need to add the starting value into the consideration, but I did. Okay, so that's basically what I would do. Okay, now let's go back. So look at the distribution again. Okay, the distribution is going to be, at least for the logarithm, is going to be normal. So the logarithm will follow the normal distribution, not the process itself. And since the logarithm is identical to a Brownian motion with drift, it will follow the distribution of the Brownian motion with drift. And that is basically it, which is actually revealing that the geometric Brownian motion, on the other hand, would follow the so-called log normal distribution. The log normal distribution occurs if the exponent of a random variable is following the normal distribution. So if the exponent will follow the normal distribution, indicating, for example, normality here of asset returns, which is a standard assumption in finance, or a lot of basically asset pricing models make the assumption of the normality of asset returns. Whether this is true or not, this is just a different issue, but again, there is the assumption. Okay, then the price of the asset will be basically follow the so-called log normal distribution, which actually would be. So keep in mind, guys, this is, I cannot stress this enough. The geometric distribution, the geometric Brownian motion does not follow the normal distribution. Its logarithm does. So the geometric Brownian motion would follow the so-called log normal distribution. Now, how to address the expectation and the variance of the geometric Brownian motion? This is something that you don't need to do. I will. Okay, so I'm going to prove that later on. However, it is already available. So if the logarithm of a random variable would follow the normal distribution, and which would be the case. All right, so you can see this over here with mean A and variance B squared, then at least its expectation. So not the expectation of the logarithm. The expectation of the logarithm would be A, but not the expectation of the random variable itself. You don't need to address it now. This can be shown relatively easily. I will use Ito lemma to prove this actually. It's easier, much easier. But again, that will be just simply just, using the transformation theorem. So it will not be big of a deal. Little integration calculus, what you would do, applying it basically on the distribution of the logarithm, because that would reverse it. So e to the power of that would be basically based on that. And this is e to the power of a plus b squared by 2, where a is the mean of the logarithm, and b squared is the variance of the logarithm. And this is it. So that's just simply it. So of course I would need to have the starting value, of course, right? And then, which is equal to 1, by the way, almost surely. So the starting value, if it's not, then you could change that, but it is equal to 1. But that's not usually the issuing price of a stock, by the way, times e to the power of the expectation, which is mu times t, so it's an a, it's mu times t here for this one, for the logarithm, and t comes after that, plus the variance by 2. The variance by 2 is sigma squared times t by 2, but if I multiply basically both expressions by t, then it should be fine. So it's actually mu times t plus sigma squared by 2 times t, and that's it. That's going to be the exponent. So this is going to be the expectation. Later I'm going to prove this using Ito's lemma, which is easier than applying just a transformation theorem, but it can be also done, so it's not big of a deal. Next, I'm going to look at the variance of the geometric Brownian motion, which there is a hint where you would simply just be able to address the variance of the random variable, where actually its logarithm would follow the normal distribution, would mean a, and variance b squared. This is the formula that you're about to see, so e to the power of 2 times the mean plus the variance of the logarithm times, and then you got this in brackets, e to the power of the variance of the logarithm minus 1. That's going to be basically in here in parentheses. It's not that big of a deal. In addition, I'm going to look at the starting value. The starting value is, of course, can be addressed to be equal to, actually to be equal to 1 almost surely. However, it's not, so if there is a drift, it's not, you can see, because the Wiener process would be it. So then if the logarithm is that, this is not basically what it would be, but it doesn't really matter, so you can simply just take that one. Okay, if it is 0, then the Brownian motion would be equal to 1. Almost surely it's a starting value, but anyway, I was keeping that. And this is e to the power of, and then you got 2 times the mean, which is mu times t, where the mean of the logarithm is mu times t. T comes after. And then plus the variance, right, which is sigma squared times t. So if you multiply both expressions by t, that should be fine. So this is 2 times the expectation, which is 2 times mu times t, plus sigma squared times the expectation, which is sigma squared times t, and that's it. And then of course this half, and then times e to the power of the variance of the logarithm, which is sigma squared times t. So I was basically writing it like this. There is too many exponents, whatever, so exp is the same notation, right? Or it's not the same notation, it's a different notation, but for the same thing. So, and minus 1, that's it, okay? And then later we're going to prove this, so that can be shown relatively easily. It's not big of a deal, but that is the mean and the variance of the geometric Brownian motion. Okay, now next I'm going to look at the maximum Wiener process. The maximum Wiener process is simply the following. Okay, so x is going to be it, and it's going to be the maximum of all the observations, you can call them observations, that the Wiener process had up to time point t. So up to time point t, we're going to look at the maximum value of the process, and that's basically what it would be at that point of time, that it had at that, up to that point of time. So basically, if it goes down, it will stay at the top, so the maximum will basically, if it goes down again. Okay, so it's only basically corresponding to that of the Wiener process if the Wiener process is strictly increasing. Okay, so here it's going to, this is how it's going to look like. So first off, I'm going to start by a path of a Wiener process. This is what you see. And then, of course, I'm going to add is basically its maximal counterpart up to a certain point of time. So here it's basically, it was a little bit greater than that. Okay, so here at this point, it was jumping here a little. It's not a jump, but you can call it like that. So it is going to stay on that level. And after that, it has increased, let's say, without loss of generality, and of course, right? Then it will stay on this top. Okay, so this is just a dash line here. Here, that one. And then from here, this point on, it will not go back down until basically the Wiener process would hit it back again, which could be the case. All right, so but up to this point, it will not change. This is just simply just the variant, the maximum of the Wiener process from this point on, and will corresponding to this value, because that was its greatest observation at this point. Okay, that can be also applied in finance, basically a lot of things, especially when you look at dynamics of basically of stocks or related to option pricing, whatever. Okay, but I'm not going to. Here it's going to be the same expectation. And as you see, you might not remember this, but the expectation of the maximum Wiener process is going to be identical to that of the reflected one. This is not clear why, but I'm going to demonstrate this result. And the reason is because, of course, they will have the same distribution. That is their answer. Okay, they're not equal, but they will have the same distribution. I'm going to make that statement first, and later on I'm going to prove that statement. So we're going to look at this statement now. Here, you're going to look at the cumulative distribution function of the maximum Wiener process, which is given by this expression. So this is the CDF, we can call it the cumulative distribution function, CDF of the maximum Wiener process at point x, small x, and that will be equal to that of the reflected Wiener process. That's the statement I'm going to make. And the reflected Wiener process, which was the absolute value, was 2 times the cumulative distribution function of the Wiener process. You can see it here. This is the cumulative distribution, CDF of the Wiener process at point small x minus 1. That was it. Okay. So this means, of course, again, I'm going to write it down because that was it. Okay. So the cumulative distribution function of the reflected process is identical to that of the maximum Wiener process. That's the statement that I'm trying to make, and I'm going to prove that statement later on. So we're going to see why this is true. Okay, but that's going to be the important one. Okay, so it has the same distribution as the absolute value. I'm not sure whether this has a name or not. Probably not. It's not normal, of course. It's not. It doesn't have a normal distribution, the fractal one. However, it will be identical to that of the maximum one. So it will have the same expectation and the same variance, right? The expectation of the reflected Wiener process was the square root of 2 times t by pi, and the variance, if we recall it correctly, I'm not sure, which is the expectation of the squares minus the square of the expectations, right? Okay, so I was adding it, but I was already calculating it, so I would not need to do it again. That was t, and that was equal to the square of that, which is 2 times t by pi. This is simply just the same issue. Okay, now why this is, again, it's quite surprising, but the distribution of the reflected Wiener process will be identical to that of the maximum Wiener process. So it doesn't really matter if you reflect the process, actually, in terms of the distribution, or you look at basically its maximum only. That will be, or having the same distribution. And I'm going to prove that statement. Before I do so, I'm going to look at the distribution of some hitting time, which is going to be a random variable. I'm going to address this. You can also call it the stopping time, I've seen it, or the waiting time. The waiting time is also a good one. It's a random variable, okay? And I'm going to define it as such. So TB is going to be the waiting time, or the hitting time, or the stopping time, which is quite similar. Okay, you can call it the stopping time. And this is going to be the point of time at which the Wiener process, because it addresses basically a stopping time on the Wiener process, where the Wiener process itself is going to hit some value exceeding it. Okay, here the value which is supposed to hit is supposed to be greater than 0 without loss of generality. That is going to be important because to show that the reflected Wiener process has the same distribution as the maximum Wiener process, it cannot be negative. So I'm going to basically just focus on some positive value that the Wiener process is supposed to hit for the very first time, and the time point at which the Wiener process hits that value at the very first time, I'm going to call this to be the hitting time of the Wiener process for that value B. So when the process hits, let's say B for the very first time, is going to be the hitting time of the process, and this is basically what it would be. So then it holds, and then again I'm going to make that statement now, that the probability that the hitting time exceeds some value, which is going to be a current point of time, so it's going to be longer than, let's say, whatever, so it's going to come after that. The probability that comes after that is going to be identical to, I mean, I'm not sure if you're familiar with that expression, but 2 times the cumulative distribution function of the Wiener process at point B minus 1 was the cumulative distribution function of the reflecting Wiener process. That was it. And this is going to be identical. That's a statement that I'm going to prove. This does not illustrate that this is the same as the cumulative distribution function of the maximum Wiener process. But that will be just, you know, I'm going to link that to the other, which is going to be just that. Okay, but that's the first statement I'm going to prove that this is going to be the case. Keep in mind that this expression is not the cumulative distribution function of the random variable capital T. This is not it. It's going to be 1 minus the distribution of that. So, I mean, when you basically solve this one, that would just give you 2 times the probability distribution of that. But this is just another issue. We'll subtract to be equal to 1, and that's it. Because the probability of that is going to be 1 minus the probability, or the cumulative distribution function of the random variable T. Capital T, by the way. Anyway, okay, so you understand what the hitting time is, and then this is not intuitive, I have to admit. So this statement is not intuitive. Why? That's why I would need to prove it. Okay, so I'm going to basically prove that statement. What you need to notice is the following. First off, I'm going to use that later on, that the Wiener process at the hitting time, so at that time point where it hits basically the value B, is going to be equal to B, at least almost surely. I should have said almost surely, which means that with probability 1, actually by definition. Why? Because the hitting time is the time point at which the Wiener process hits the value B for the very first time. So where value B is hit basically at that point of time first. So at that point of time, the process must be equal to that, of course, because otherwise that would not be hit. Okay, it doesn't necessarily mean that it cannot be basically in the later point of time, could not be equal to B, to come back to B again, but at that point of time, it must be actually equal to B, at least almost surely, by definition, by the way. Now, this comes first, but later on, I'm going to come back to that. So, in order to show the statement, I'm going to look at the conditional probability, a conditional probability, where the Wiener process, so the probability of the Wiener process being greater than B, given that the hitting time was already happening. So T is a current point of time, some point of time, and the Wiener process is being greater than that, or probability of that, given that basically the process has already hit actually that, okay, is going to be the conditional probability that I'm referring to. Now, the conditional probability by definition is going to be the probability of the intersection of the 2 events. So both events must be true. Okay, so this one, that the Wiener process is greater than B at that point of time, and that the hitting time was prior, which is actually it's not equivalent, but the intersection of the 2. I'm going to address it later on, but that's basically what it is. So the conditional probability is the joint probability divided by the marginal probability of the condition, and the condition is that the hitting time was prior. Okay, so if I refer to that basically time point t to be the current point of time, that basically the hitting time point was prior. Anyway, okay, so I'm going to finish that statement because I'm going to look at that one. So first off, you need to understand that the intersection of the two events, whereas the Wiener process is at time point t, which is the current point of time, is already greater than b. Now, if it's already greater than b, which means that it already has passed b. Now, if it has passed b at time point t, which means that at time point t, the hitting time must be happening prior. So at basically in the previous point of time, this already happened, right? If the process is already greater than b, then it has hidden, it basically has hit, sorry, basically that value b to which basically hitting time is referring to. And so that must be prior, right? It must make sense. So if it's already greater than a certain value, it must be hitting that certain value in the previous point of time already, right? So this is just actually the subset of that, because if you know that basically the process is already greater than b, then we already know that the hitting time was prior, because otherwise it would not be greater than b. So if this is true, then this is also true. So therefore, the probability of the intersection degenerates to the probability that the Wiener process is already greater than b, because if it's already greater than b, what we definitely know for sure, at least with probability 1, is that it was basically hitting value b already, okay, because otherwise it would not be greater than that. Okay, so the hitting time was prior, that's for sure. Okay, so if this is true, this is also true, right? So that means that this is a subset actually here. Okay, so that's basically the implication what we got already. Anyways, okay, so and then we're going to divide it by the probability of the condition, and then we're going to talk about that a little bit. So we're not done. We need to talk about that in a moment, but that's just what we'll have at least this far. And the second statement that I'm going to make about this conditional probability is, and this is what it's going to be, is that this is going to correspond to, first off, I'm going to write it down. So I'm writing down the condition, here it is, and then I got basically the process at time point t. Now, here comes this equation here. I'm going to subtract basically b on both sides of the inequality, on the left as well as on the right-hand side of the inequality. If I do this on the left-hand side of the inequality, then I'm going to get basically the process at time, okay, I'm doing it here, so let's do it first on a time point. Okay, so what I'm going to do again, so take a look at this inequality, and I'm going to subtract b on both sides. Why? This comes next. Okay, so if I do this, then this is going to be the current observation or the current value of the process minus b being greater than 0. And since, and this is what you need to see, b is supposed to be, or let's say the process, okay, which you're going to see first, okay, at the hitting time is equal to b. You can simply just replace it, okay, which I did. All right. And this is basically the increment of the Wiener process at time point t with respect to basically the hitting time. So what happens after the process has hit, basically value b. Now, this increment being greater than 0 is the probability of that. Again, it doesn't depend on anything. Okay, this is the condition, so t must be greater than that. So that is going to be its future increment after the hitting time. The probability of that is going to be 0.5. That's it. Why? Because, and that's basically it, okay, the increment is Gaussian with mean 0. Mean 0 means that its density is going to be symmetric with respect to the y-axis. So half of the area is going to be on the right and half of the area is going to be on the left-hand side of the y-axis. So this is basically where 0 is. And yeah, so that's basically it, right? So any Gaussian random variable which has the mean 0, the probability of that being greater than 0 is going to be actually 0.5. All right, so that's it. So again, since this is going to be, since it's a Gaussian, right? I mean, of course, we'll have basically the increment here. And this is going to be having the mean 0, which is illustrating that, yeah, this probability is going to be 0.5. Okay? So on the one hand, this is going to be, this probability is 0.5, and this is equal to that, you can see. So then the two actually must be equal to each other, which means that the ratio of these two is going to be 0.5. And now we need to solve this equation, or you can see that here, for the probability that the heating time is prior to time point t, which is going to be 2 times the, actually, this expression, which you see. Okay, so that is what you were end up with. This is one prior result we just shown. Now, this is not what I wanted to show, because I wanted to calculate basically the probability of its complement, whereas the probability of a complement, whereas the heating time would not be less than t, which means that it is at least, so you need to wait at least up to time point t or longer until the process hits basically a certain value. So the probability of waiting longer than t for the process to hit basically that is going to be the probability of its complement, right? 1 minus the probability basically of that. This is equal to the probability of its complement. And so 1 minus that one, okay, which is here, is going to be 1 minus 2 times this expression, which is you were about to see here. So I was basically just copying it as you would see, okay? And then what we do later on, I'm going to play with that a little bit because I want to change that too. I want to express this basically by using 1 minus actually the probability of its complement, because again, the probability that the Wiener process is going to be greater than b is 1 minus the probability that it is not, right? So you see, okay? And here I'm going to play with those expressions a little bit. So you got 2 times the probability that the Wiener process is not greater than b. And then you got plus 1 minus 2, which is equal to minus 1. So this is going to yield 2 times the probability that the Wiener process is not greater than b, minus 1, because plus 1 minus 2 was basically just that. Now this sounds familiar, right? Because again, we're going to put those things together into the following corollary. So let me just basically make the statement again. The statement is that the probability that the heating time, or let's say the waiting time, is greater than the current point of time. So you have to wait longer. Now, since t is, capital T, of course, is a continuous random variable, because its cumulative distribution function can be addressed by actually that of a continuous random variable, at least. Okay, continuous state random variable, so time point t, the Wiener process, is also continuous, at least almost surely, regarding its path, but I'm not talking about basically the path, I'm talking about basically the state. Okay, so since it's Gaussian right away, it is going to be identical to this expression. There is no difference basically between the two. Okay, which again, I want to stress here. That's exactly the same. Again, because the random variable, capital T, is supposedly be a continuous random variable in terms of its state. So the value is that basically what it can take. Okay, so that's statement number 1. And this is equal to the cumulative distribution function, or reflective Wiener process, which has been already addressed. That's statement number 1. Number 2, this probability where the waiting time or the hitting time exceeding some time point, current time point, basically time point t, is going to be, and that is a statement that I'm going to make first, and then I'm going to explain it later on, the probability that basically the maximum value up to that point, so up to time point t, does not exceeding it. Okay, because if you have to wait longer, right, then whatever the maximum value of the process was is definitely right, is definitely not greater than basically the value b. Otherwise, if it was greater, then value b would have been already hit, right? So but it isn't it up to that point, but it did not happen, right? So if this is not basically happening, that the process is hitting the value, because you have to wait longer, okay, up to time point t, so the hitting time is greater than time point t, which means that up to time point t, the process has not reached the value b. If the process has not reached the value b, then its maximum has not reached the value b either, or reached or exceeded basically the value, which it is. Okay, so that's it. Okay, it should be actually less than b in this case, but this function or this random variable is also continuous one. It doesn't really matter whether it's basically less or equal to, and yeah, those two are equivalent. Okay, so again, if the waiting time for the process to reach b is longer than the current point of time t, then this means that at the current point of time the process has not hit basically value b, because otherwise it would have, you know, the waiting time would be not greater than that. And if the maximum of the process is less than b, again, it doesn't really matter if it's less than or equal to, that this means that the current point of time is basically not, or basically the hitting time has not reached the current point of time yet. That was the issue which I wanted to make here. Okay, yeah, that's it. Okay, so that is basically equivalent. Again, do not let this basically distract you from the fact that for maximum to be less than b, is the probability of that is going to be equal to the probability that the maximum is not greater than b, less than equal to, because this is also a continuous one, a continuous random variable, by the way. And now you see that these two are equal. So the probability of this happening, which means that the maximum is not greater than b, this is the cumulative distribution function of the maximum Wiener process at that point of time, is going to be the same as this expression. So this is the cumulative distribution function of that, and this proves the statement that I was making, which means that the cumulative distribution function of the maximum Wiener process at point b is equal to the cumulative distribution function of the reflecting Wiener process at point b, okay, which means that the probability that the reflecting Wiener process is not greater than that. So that's one way to basically to crack actually the distribution of a maximum. And yeah, that's pretty much it, right? Because again, you can also do this for the minimum, by the way, but I'm not going to address that. This is something which you might do yourself. Okay, guys, yeah, that was it for today. It's going to be shorter because the lecture is online, but we already had 1,820 pages, so that should be fine for today. But next time it's going to be 3 hours again. So when we meet, it's going to be, actually, I'm going to continue here. Okay, so I wanted to back up some basic properties that the Wiener process has, and that's basically what I would do. I would recommend you to, for exercise, calculating basically means and variances and so forth. For example, for the Brownian bridge, and yeah. those are the things that you would need to look at. All right, guys. Thank you very much.